All right, good morning. Happy Thursday. The sun's out today. Yesterday was kind of dreary. It was kind of fun though. I've got my two little guys, and the youngest one he'll be 3, or no, just kidding. He'll be 2 on June 3rd. And so last year he was, like 9 months old at this point, and even last summer and stuff, he was still really little. So the idea of rain isn't something that he'd really experienced before. So as it was raining yesterday and I was running him into daycare or out of daycare, he was like half confused, half amused, overlapped with just being upset that he kept getting wet. It was real funny to watch. So, we just know that it happens. And for him, it was totally new. So, but today the sun's out and I like that. So, good. I know our ski team is going up for state, so good luck to everybody there. And I know we've got just we're moving forward with a lot of things here. So our plan for today is that we're going to talk about Feynman diagrams. And so I'm going to do that a little bit with a PowerPoint and talk through some of that. And then also I'll show you kind of written on here how it'll work. And so Feynman diagrams allow us to visualize what's happening in these teeny tiny interactions. And so it ends up being sort of a goofy deal. It's taking something that we can't fully see just on, can't just be like, oh, look, pink, oh, this is what happened. And then putting some visualization to it. And so we'll get into kind of how it sets up, all the different pieces of that. I'm going to share my screen with you. And before we jump over to the PowerPoint, I just want to show you in Schoology a couple things that we have that can be helpful. If we go into our Q3 and go down to this week of March 8th to the 12th, I can't believe we're already at this point in March. We have in the videos, etc., it has the full PowerPoint of the things that I'm doing. And it has a particle physics glossary that helps with all of the verbiage that we're using. And so if, as you're working on, there's an assignment in there. I think I still need to add the date on it that it'll be due. It'll be due next week when you take the quiz. But as you're looking at putting all the pieces together, this is a helpful way to just sort of know, we're talking about all of these different words that are completely new and make little sense sometimes. And so it's a nice little kind of concise place that has all of it. And so that's in there in the videos, etc. And then there's also a link that's a YouTube video that goes through just all the different sections. And so I combined them all into one. I had a folder and whatever, it was a mess. So it's all in one. So know that there's different sections. You can kind of follow through and get the different sections on there and be in good shape. So know that all of those are options and things that you have available to you while you're working this through. So for us, for what we're looking at here, we're going to start with Feynman. I got to turn. Go back here. All right. So the idea of a Feynman diagram is that we have, it's like I said, it's this visual representation of the interactions, and it helps kind of predict the probability of different outcomes within these particle collisions. So it's the way that the particles interact with each other. And it's a goofy diagram because it sets up space on the y-axis and time on the x-axis. And so at the bottom here, it says some books switch space and time. The IB presentation is shown as above. So the IB in testing and stuff, we'll use the time on the x and space on the y. Do think in our text, in our Oxford book, they do switch it some of the times. The Oxford book isn't actually published by the IB. It's published by an external company in line with the IB. So what happens, so if you watch the side of the screen here, you have 2 electrons approaching each other. So they go up and back, up and back. And so this is the motion of what's happening. They're not moving to the side. They're just moving up and back. So if we just had these two going back and forth, it would look like that if it was just following the path that was going along with it. Bubble of ignorance we talk about is what's happening as they approach, and it's sort of ignorance, but sort of we do have some ideas on what's going on in there. However, if we continue here, so you would have them go together and then go apart. And so if we just were talking about where things were, so the y-axis, this is what we would see. However, we also know that time is going by at the same, concurrently with the motion. And so what's happening here, the way that this Feynman diagram will look is like this, where we have the back and forth going, but it also is indicating that time is passing while the particles are going up and down. So when you look at this, it looks like, just on quick, if everything was space, so if we had where it was in the x-axis, where it was in the y-axis, then it would be that it's traveling to the side, they're both traveling to the side, they collide and they both separate. But we don't have a spatial measurement on the x-axis. We have a time measurement on the x-axis. So when these are at an angle, the motion of the electrons here are still up and down. It's just up and down. But the angle of this indicates that time is passing while this is going on. So we have to take just a mental shift of what we normally would expect in the way that these graphs appear. Let's see. So this one here, we'll label what these are on each one. Sometimes it's the whole particle, like an electron. Many times we'll do some stuff with quark configuration in a bit, and so you'll have each of the quarks labeled in there, and by the quark combination you can determine whether it's a proton or a neutron, potentially something else, but that would be given to you in what we're doing. So the Feynman diagram allows us to see what's actually happening in the midst of all of this. That time axis, the piece that just came up, it allows us to draw the reaction spread out over time. So it allows us to be able to see what's actually occurring and make it clear as to what's happening. So we have some different symbols that we have here. So we have our different particles. If you have a particle in itself, so this could be a single quark, it could be a proton, neutron, it could be an electron. Any of those things are the particles, and they're drawn with a straight line with an arrow at the end. We'll talk about what the arrows mean in a little bit. They're a little bit counterintuitive. The electromagnetic and weak exchange particles are drawn with a wiggly line like is in the orange one there. And then the strong exchange particles for our gluons, those are going to be in it's a curly kind of weird looking line. The thing that's really cool about doing Feynman diagrams is they look kind of ridiculous, and to be able to talk about them knowledgeably, I don't know, it just makes you look smart. So when you're working on this, work on it in a place that is a little bit, you've got people looking over your shoulder and they're like, what are you doing? What are you doing? And you're like, just doing some nuclear physics, no big deal. One of my favorite things to do, my husband used to work in baseball, and so he would leave early March and not get back until Labor Day usually. And so I would spend the summer wherever he was, but we'd have March, April, and May of where he'd be in Florida doing spring training or wherever his team was. And so I'd spend a lot of time on airplanes, and one of my favorite things to do would just like work through all the stuff that I was doing for the week sitting there, because someone next to me is like, what are you doing? And I'm like, just a little physics. I don't know. It just kind of throws people off a little bit. It's kind of fun. So there you go. While you're working on this, sit somewhere that you can have people notice it. So with the electromagnetic exchange particle and the weak exchange particles have the same wavy symbol. discussion that they come from a single, it's called the electroweak force. So it's a sort of a combination of the two. Therefore, they can be represented as such. We'll see the weak force in our transitions, particularly when we're dealing with beta decay. So let's look at what's happening here. In this one, it says complete the complete Feynman diagram showing the repulsion of two electrons looks like this. And so you have the electrons that are going back, and one's coming down, one's going up. They meet and collide, and then they spread out back apart from each other. The force that propagates the electromagnetic force is your photon. So remember, when we talk about our force particles, that while this force is occurring, it's propagated by the particle of a photon. And so this is what so you have these two coming together, and then that photon is the force, the propagation of that force, and then they are separating back out. Again, it's time that's going by that allows this to spread out, as opposed to the motion of that being spread out like that. If we just had an electron that's emitting a photon, we would have something that looks like this. So that electron allows that photon to go out. So when we're talking about, back when we talked about energy levels, and the energy levels would drop from one energy level to another, and a photon would be emitted, this would be something this would be a diagram of that. So the electron in its own is just emitting the photon. So here's where it gets goofy with our arrows. In Feynman diagrams, antimatter points backward in time. It does not mean it's going backward in time. Just is an indication of that it is an antiparticle instead of a regular particle. So the arrow is pointing backward, but time is still moving forward. Again, it's sort of goofy with what we have going on here. So we would draw this. Here's our antiparticles. Anytime you see a backward arrow, it is indicating that it is an antiparticle. Again, it does not mean that time is going backward. This antiparticle, so it's a positron, an anti-electron, is still starting at the top, coming down, and repelling back. Time is still traveling along the horizontal axis there. And because the arrow is designated as backward, it is designating that it is an antiparticle. I know, it's goofy. Another example, we had talked about that electron emitting a photon. And this would be that same diagram, but instead of an electron, it's an anti-electron, a positron, and it would look like this. Again, as time is going by, time is still traveling over to the right, from the left to the right. The particle is, in this situation, is traveling from up here, down, and then back up. The only thing that's different is that the arrow is pointing backward. The arrow pointing backward does not actually indicate direction, but it indicates that we have an antiparticle here. Goofy, I know. Super goofy. All right, so here's some other goofy stuff that happens. You know how we talk about mass and energy and how those things can go hand in hand? You can have some energy that will produce mass. And in this case, you would have a matter-antimatter pair. So what we have with this is we have a photon that is taking that energy and producing an electron and a positron. Time is still going from left to right, so that photon is moving. As it separates into an electron and a positron, those two particles move apart from each other, and they're represented with their arrows. Remember, the arrow pointing in a kind of normal direction is your electron, it's your particle, and the arrow pointing in the negative direction, or in the backward direction, is your antiparticle. It does not, they're both still just moving up and down here. We also can do that in the reverse. If you have an electron and a positron, and they can annihilate each other to become energy. And so in this situation, you have, again, the motion that we're talking about is only up and down. It's time that's spreading out the way that we're drawing it. So you have your positron at the top, your electron at the bottom. They come together and they meet. They annihilate each other, become energy, and that energy would continue forward. So not only are the drawings goofy, but we're also getting into some of the pieces that can occur within the nuclear physics that kind of make us go, what? What are you even talking about? Again, in what we're doing with nuclear physics, we're very much in the observation stage, the asking questions stage, the being able to identify what's happening, possibly predict what's happening. The Feynman diagrams help to do that. The conservation laws help to do that. But so much of where we are as a scientific community is kind of in that beginning stages of what we can do, as opposed to how we can make it useful for us. So a lot of times, like I said, in beta decay is where we're going to see our weak nuclear forces more. And so in this one, we have a down quark turning into an up quark. And so we're going from a neutron of up, down, down to a proton of up, up, down. And it doesn't matter the order in which we list those. You can say down, up, down if you want. Oh, hey, what's going on here? We'll do that later. Do not want to reinstall Chrome. There we go. So this is looking at just that single, oh, go back, that single particle change on there. One later will show you kind of the rest of that. In that, we have a W minus. That's our weak nuclear force. And so it goes from a down quark. In that interaction, we have an up quark that is now, that it has transitioned to. And in the process of that, by the weak nuclear force, there's also your electron and anti-neutrino in the electron family that is released. And so you can map out the process, including all the different things that are happening, and then conservation rules, you can predict what is happening within that. So here. So if we look at this Feynman diagram here, we have an up quark, and it continues with an up quark. But in the process, we have a gluon, so our strong nuclear force. See how that's drawn with the curly lines there. And then we have a down and an anti-down quark that are being created from that strong force. And so if we have on each of these, we have up, up, and down. And if you look at the red ones that are on there, the down quark stays as a down quark, the up quark stays as an up quark, and they don't have anything that's changing in there. They don't have anything that's releasing or anything that's going on. It's that single up quark that's at the bottom. We still have, if we have an up, up, down, we still have a proton. But in this situation, there's some energy release, as well as a down quark and an anti-down quark that are being created here. That just talks about what we have. Quarks cannot exist by themselves, and so the two quarks produced above will actually very quickly annihilate. They won't be there. They may be joined in with something else. They may go back to energy. You've got kind of different options that'll happen with it, but they will not stay as individual quarks very long. Look at this one. So we have a down quark that's going into an up quark. And so if we have a down quark going into an up quark, we're going from a neutron into a proton. So up, down, down, and up, down, up. So the down is switching back into an up. And with that, we have our weak nuclear force, and that's going to kind of propagate the emission of the electron and the antineutrino here. Remember when we're talking about our beta decay, and we'll always have that electron and antineutrino, or our positron and neutrino. And so anytime something like this occurs, both of those particles will be emitted in what's happening. And again, anytime that occurs, that antiparticle will have that arrow drawn backward. And so we'll see this combination a lot. If it were going up, if it started with an up quark and ended in a down quark, the difference would be is we would have a positron for the instead of the electron, and we would have a regular neutrino instead of the antineutrino. And so on these red line, these ones do have the red lines on here where we can see the other, that the up quark, so the proton and the neutron are both comprised of the 3 quarks. The up quark stays the same through the whole process. The down quark that's in the middle there stays the same through the whole process. The only quark that is changing is the down quark from the neutrino, or from the neutron, is changing into an up quark, creating the proton. Again, this is what's occurring in beta decay. So it's visualizing what's happening. Also remember that all we're looking at here is a sliding up and down. Time is what's spreading it out, not other positioning. This is what our equation would look like for that. So write the reaction, including the neutrino for beta decay. This is one that you should just commit to memory for what you're doing. And then with your Feynman diagram here. So what we would say with this is we would draw, the proton is up, up, down. And so we would draw those the other ones, the other quarks that stay consistent in it, those will go in there as well. But then that third line of quarks goes from that up in the proton, changing into a down to create a neutron. You will not need to be able to think, oh, I wonder what force is going to propagate this. Should be a W plus, it'll usually give you what's happening, and you'll have to be able to describe what's going on. The only one that would be something that would need to be drawn would be like if that information was given. So it might say that you have a proton that decays, like it's written here, says, write the reaction for your beta positive decay and then draw the Feynman diagram for that. It would say that the force propagating it is a W plus or a W minus or whatever you have. So you don't have to just magically know what kind of force would be there for that. All right, so a question that could occur this is taken from one of the exams. It says the Feynman diagram below represents beta decay via the weak interaction process. And then it's asking, funny, I just said we don't have to do that part. I've never seen this part actually asked, but it says determine whether the virtual particle produced representing the Feynman diagram is W plus, W minus, or Z naught boson. So we go back here. When we have so the way that you can tell that is when we have the positron that's being produced, we have a W plus. If you go back, let's see if I can go back here. And when we had the electron, it's W minus. So how we do it, we'll jump ahead. There we go. So state what is meant by a virtual particle. So those are our force particles that we have that are that are propagating the force between the interaction. And then the virtual particle in the process, represented by the Feynman diagram here. Because we have an electron, it has a negative charge. It'll be a W with a negative sign on that one. Yeah, short range of influence, and then propagates that force. And then the particle goes with the charge. Oh, there we go. End of slideshow. Cool. So again, keep in mind, I'm going to click on here for just a moment. Move this way. Keep in mind that when we're talking about our Feynman diagrams, the particle motion is still just up and down. And so if we talk like those first ones that we had, if these are two electrons and they're up and down here, we have our space that goes right here. And space and position, it's that general idea that where something is. And then we have our time that's passing by as it does that. And so the only thing, if we just had space, we would just draw that it's going up and back. But because we have time that's passing in the process, as it comes down, time is also going on. So we would say we have our electron here, that it's going there. So it's going down, but time is passing. This one's going up, but time is passing. We have our photon emission. Sorry, that's a little, I drew those too tight. And then from there, this one, that photon propagates the electromagnetic force. So we would have that. And then we have that that's happening as well. Again, even though that's drawn off to the side, the motion that's actually happening here with the electrons is just back and forth. So we have to think about that and keep that in mind with what we're doing with each of these. Any questions? Presenting here. It's a lot to take in. And the thing that I like about it is it really forces us to have to think differently and to think about the things that might be happening, that could be happening, that are happening, that we just don't know the details on yet. I like it because most people, you know, when we talk about like E equals MC squared, people are super familiar with that equation, but have no idea what it means. Well, we know what's being discussed there. With this, people talk about like, oh yeah, particles, oh quarks, and like make jokes about it. If you watch the video that I have up there, my son tells a quark joke, and so like we have each of those things, and people, just general population, have very, very little idea about it. So I always like when we get to this point because we're talking about things that really are on the edge of what is known. And it just helps expand our minds into what might be. So thanks for going through it with me. So here's where we're at. We will be quizzing next Wednesday. We've gone through all of the pieces here. I have 2 more sections of the kind of the overview to put up, the conservation laws piece and then the Feynman diagrams piece. And so what we'll do on Tuesday is we're going to recap everything. We'll go through and I'll take questions on those pieces. We'll look at the overall diagrams that you draw that kind of put all the pieces together, and then hopefully get to a point that things are making sense. The thing that is difficult about this topic is it's pretty mind-blowing. It's like, what in the world is going on? The thing that's nice about it is that the questions that are asked are usually really focused, to the point so much that they start to get repetitive as we're going through. It's like, okay, it's beta decay, I get it. I can write about it. I can tell you what's happening. I can draw a Feynman diagram about it. And so because we're looking at each of those pieces as you're looking through it, this is actually when we do take the exam, it's one of the parts of the exam that most people do best on, because this kind of the ability to ask questions about it is pretty narrow. So if you're sitting there saying like, this is crazy, how am I going to take a quiz on it? You're probably going to be just fine. So that quiz will be due next Wednesday. I'll get all of that into Schoology today. And then everything will be due on Wednesday, and you'll take that quiz on Wednesday. And then we're going to be wrapping up with this unit and heading into taking the test. So We are moving along. After this, we'll get into topic 8, which gets into energy and power supply. Another fascinating thing. It kind of starts to put to practice some of the ways that physics can be utilized for different types of energy. And then we'll kind of see that one can be different time lengths. And so we'll kind of see where that brings us and how much time we have left, and then what units we do after that. I'm hoping to get to talk about some of the stuff that we had to skip over earlier this year, just because it's cool stuff. So we'll get there. Y'all are doing an awesome job. Enjoy the sunshine today, and I will see you next week. Thanks. Bye-bye.
Thank you.